Hello everyone and welcome back to the C++ 3D game tutorial series. In this 37th video tutorial, we will see how to make a 3D terrain. In particular, we will see how to generate the terrain mesh, how to render a 3D terrain through the Vertex shader and the so-called height map, and in the end, we will see how to enlighten and color the surface of our terrain. As always, we will face three main parts: requirements, design, and implementation of all the necessary things to make a 3D terrain. So let's start with the requirements. We need a C++ IDE. In this series we use Visual Studio 2019 Community. The target platform is Windows. The target graphics API is DirectX 11. And last but not least, a bit of knowledge of C++ programming language is recommended. Now we can start the design part. In order to create our 3D terrain, we have to face four main phases: the generation of the terrain mesh, the rendering of the 3D surface of the terrain through the vertex shader and the height map, the computing of normals through the height map, and in the end, the coloring of the surface of our terrain. Before to start with the first phase though, let's make some premises. In order to render an height map based 3D terrain, we have to create a mesh to use as foundation. But first of all, what is an height map? In few words, an height map is nothing more than a texture in which each pixel contains an height value. Our goal is to create a quadrilateral flat mesh like this one, in which each vertex should correspond to each pixel of the height map. Once we have this mesh and we render it, during the execution of the vertex shader we should retrieve for each vertex an height value from the height map and use it to displace the vertex of our flat mesh along the y-axis. That said, let's start with the generation of the terrain mesh. As we have just said, we have to create a quadrilateral flat mesh. To do that, we need to create a vertex buffer and an index buffer, as we have already done for our generic mesh. Then we have to compute all the necessary vertices. Let's suppose we want to create a mesh with 3 quads along both the x and y axes. Such mesh is composed by 4 vertices along, again, both the x and y axis, for a total of 4 per 4 vertices, and so 16 vertices. As we have said, a vertex should correspond to a pixel of the height map, so in general we should have an amount of vertices in the order of 512, 1024, and so on, along both the axes. Here we are using 4 vertices to understand the concept. Let's see how to compute such vertices. For each vertex along the x-axis and for each vertex along the y-axis, we have to place the data of a vertex inside the list of vertices, that, as we have seen a few moments ago, should be a list of 16 vertices. But in what position we should place the vertex precisely? Let's try to compute the position of the 10th vertex. Such vertex must be placed in the y per 4 plus x position. So, first of all, we have to compute the amount of vertices of the previous rows, that is y per 4, so 2 per 4 vertices, that in this case is 8. And once we have this amount, we don't have to do nothing but sum the amount of vertices along the current row, that is the x value. In this case, x should be equivalent to 1. In the end, the result is 9, that is the index of the 10th vertex. So far so good. Now that we know where to place the vertex inside the list, let's see how to compute its coordinate. Let's take again as example the 10th vertex. In order to create the most generic mesh possible, we have to provide a mesh of a unit size, so a size of 1 unit along both the x and y axis. In this way, we are able to scale our mesh easily with any scale matrix. In order to create such mesh, we have to compute the coordinate of our 10th vertex in this way. We have to simply divide the x value by the amount of quads along the x-axis, in this case 3. The same thing is applied for the y value that is placed instead along the z-axis. The y value of all the vertices of our mesh is ignored since it will be provided from the height map as we have discussed few moments ago. So let's place a 0 value in such a way to make a flat mesh. Since the values of the coordinate of our vertices go from 0 to 1, the same values can be applied without issues to the texture coordinate of those vertices. So far so good. At this point we have to create the index buffer. We know that the index buffer is necessary to render meshes without repeat the same vertices in the list of vertices in such a way to save memory. We also know that, using the triangle list mode, a triangle is defined by placing 3 indices one after the other in sequence, where each index corresponds to a vertex in the list of vertices. Knowing that, we can compute the list of indices in this way. For each quad, we store 6 indices, 3 for the first triangle, in this case shown in red, and other 3 indices for the second triangle, here shown in blue. The formula to compute the indices is shown in this code snippet. That is obviously the same formula used to compute the indices in which to place the vertices in the list of vertices. Let's compute the indices of the first triangle. And in the end, let's compute the indices of the second triangle. Very well, at this point the base terrain mesh is generated. Let's go ahead and let's face the concrete rendering of the 3D terrain through the height map. So what is an height map? As we have just seen, an height map is nothing more than a texture in which each pixel contains an height value. Indeed, this kind of map is generally shown as a black and white picture, where the black color corresponds to the minimum height value that equals to 0, and the white color corresponds to the maximum height value that equals to 1. Now that we know generally what is a height map, another question comes spontaneously. How can we render a terrain through this kind of map? The answer is through the Vertex shader, in particular through a specific feature called Vertex texture fetching. As the name suggests, Vertex texture fetching is a feature that allows us to fetch texture data from the Vertex shader. That is a really cool feature because it allows to modify the coordinate of the vertices by using the data retrieved from the texture in the Vertex shader. This modification of the vertex is also called vertex displacement. In our case, vertex texture fetching allows to take the height value from the height map and displace a vertex of our terrain mesh along the y-axis of a certain amount based on the height value. That's why we have ignored the y value during the generation of the terrain mesh, since it is provided by the height map. Very well, at the end of this phase our terrain should start to take form. Obviously that's not enough. What are we missing here? The normals. As we already know, the normals help us to compute the lighting correctly. The problem now is, how can we compute the normals in this case? By using the height map, without deeping a lot the math behind it. By using the so-called central difference approximation method, we can compute the normal from our height map by taking the neighbor pixels of the pixel placed at the current texture coordinate. In particular, the top, the bottom, the left and the right pixels. Once we have fetched the height values of those pixels, the formula to compute the normal is the following. Once we have this normal, we can use it in our lighting computation, and we should get this result. Very well. The last part we are missing is the coloring of the surface. The coloring is done in the same way we have done in the previous tutorials. Let's place, for example, a grass texture over the surface of our terrain. We should get this result. Unfortunately, this coloring could not be good enough. What can we do to improve this aspect? We could apply the grass texture only in the parts of the terrain in which we have the ground surface, and we could apply a rock texture instead over the surface of the walls, like in this case. At this point, how can we create such effect? By using the dot product. As we have already seen in the lighting tutorials, the dot product between two unit vectors returns the cosine of the angle between the two vectors. So let's make the dot product between the y-axis and the normal of the point of the surface of our terrain. In general, the y-axis is the normal of the ground surface. So if the result is 1, the normal and the y-axis coincide. In this case, we can place the grass texture. If the result is less than 1 instead, the surface starts to curve, and in that case we can place the rock texture. Using this logic, we can get this result. Unfortunately, the result is not so good yet, so let's tune a bit the threshold. For example, we can use 0.8 as a threshold instead of 1. In this case, the effect is surely better than the previous one. But we can do even better. We can blend the two textures in such a way to create a seamless effect, like in this case. The blending can be performed using this formula that makes a linear interpolation between the two textures starting from a minimum threshold and arriving to a maximum threshold. Using this formula we can finally obtain the final result. If you have questions, doubts, or comments about this topic, don't hesitate to leave them in the comment section of this video or in the Discord server. The link to the Discord server is available in the video description. Also, if you find these tutorials helpful, please consider to support their development on Patreon. Every single contribution makes the difference, regardless the amount. Very well, we have gathered all the necessary information to start the implementation. As first thing, let's go to the entity folder and let's add a new class. Let's call it terrain component. As usual, let's add the constructor and destructor methods. Obviously, let's inherit from the component class. At this point, we can start to add the first attributes. that is the height map texture. Let's also add its setter and getter methods. Let's also add a further vector 3D attribute that we can call size, that should provide the size of our terrain in the game world. Let's set 512 units for the width and depth, and 100 units for the height. Of course, let's give to the user the possibility to change this size through the setter and getter methods. Don't forget to add the onCreateInternal method. So far, so good. Now let's go to the graphics engine header file and let's add a set of terrain components. Of course, don't forget to add a forward declaration to the terrain component class in the prerequisites header file. At this point, in the graphics engine C++ file, let's go to the add component method, and here let's add a terrain component as we have already done with the previous types of components. Let's handle only one terrain component for now, in order to simplify the work a bit. Let's also remove the component as we have already done previously. Very well, now our terrain component is ready. We can start to go to the terrain component header file and we can add an important method called generate terrain mesh. This is the method in which we have to generate the quadrilateral flat mesh that we have already seen in the introduction. Let's start by defining the number of vertices along the width of 512 vertices. Let's do the same thing for the height. Let's also define the number of quads inside the mesh, that is simply the number of vertices minus 1. Here we have to allocate the list of vertices, where each vertex is defined by the vertex mesh data structure. The total number of vertices is nothing more than the multiplication between the number of vertices along the width and the number of vertices along the height. Let's also allocate the list of indices, whose size is the total number of quotes multiplied by 6. 6 is the number of indices required to render a single quote, as we have already seen in the introduction. It's arrived the time to make the loop. And place each vertex in a specific position that can be computed through the formula already faced in the introduction, that is y per number of vertices along the x-axis, w plus x. Then, since we want to make a unit-size mesh, in order to be easy to scale, the coordinates of the various vertices should be computed in this way. For the x value, we should divide the x value of the loop by the number of quotes along the x-axis. For the y value, we should set a 0 value, and for the z value, instead, we should divide the y value of the loop by the number of quotes along the y-axis. As we have already seen in the introduction, the same procedure can be applied for the texture coordinate, that is a vector 2D attribute. The last three vector 3D attributes are the normal, tangent, and bitangent vectors that we should not provide here. At this point, we have to compute the indices. So if we are at the top left vertex of each quad, we can compute the list of indices of that quad. The way in which to compute the indices has been already faced in the introduction, and it is always based on the formula used to compute the position in which to place the various vertices inside the list of vertices. We define firstly the three indices of the first triangle. And in the end, we define the other three indices of the second triangle. That's all. Now let's define in the header file the vertex and the index buffer for our terrain mesh. Let's also create the vertex buffer from the render system and let's pass the data just computed. Let's do the same thing for the index buffer. So far so good. Our vertex and index buffers are ready. The next step to do is to create the constant buffer, for which we can pass the data of our terrain to the shader. Let's also add an update data method through which we can pass externally the data to the constant buffer of our terrain. And always in the update data method, if we pass the data and the constant buffer hasn't been created yet, let's create it. Otherwise, let's simply update its internal data. Let's fix the parameter of update method of the constant buffer class that in this moment it allows us to pass a constant buffer by copy and not by reference. And here we go. In the end, let's start the generation of the terrain mesh in the onCreate internal method. What else? Well, we should also handle here the vertex and the pixel shaders of our terrain. So let's add two attributes, so the vertex and pixel shaders. And in the generate terrain mesh method, let's create them. Let's compile our shaders through the terrain.hlsl file. At this point, let's effectively create the terrain.hlsl file in the shaders folder. For now, let's copy and paste the content of my material shader. As first thing, let's create another data structure called terrain data. Here we should place all the data related to our terrain. In particular, we need the size of our terrain in the game world and the width or the height of our height map. Let's define an attribute of type terrain data in our constant structure. What can we do now? We can move the texture above the vertex shader and we can rename it in height map. So let's finally start to displace our vertices through the usage of the height map. The first thing to do is to define the texel size, that is the size of a single pixel in the texture area whose size goes from 0 to 1. Then we can finally exploit the vertex texture fetching feature by using the height texture and calling the sample level method. That allows to fetch data from a specific map of our texture. In our case, we have only one map at index 0. Now that we have the height, we can finally compute the effective position of our vertex in the game world. So we can take the original position from our vertex, that let's remember its position is in the range 0, 1, and we can multiply it with the world size of the terrain. When we have to compute the y value, let's use the height fetched from the texture. In the pixel shader, let's use a simple white color as the surface color. Very well, let's come back to the graphics engine C++ file and in the update method let's start to render our terrain. So let's loop over the set of terrains and for each terrain let's retrieve the WOD matrix and let's place it in the constant data structure. Then we should create the terrain data structure even C++ side. So let's go to the top and let's create it. In the end, let's add a terrain data structure as attribute in the custom data structure, as we have already done in the terrain shader. Good, so let's store the size of the terrain and the size of the height map. Unfortunately, in this moment we are not able to retrieve the size of the texture. So let's go to the texture header file and let's retrieve the texture 2D reference. Then we can come back to the graphics engine C++ file and we can finally retrieve the width of the texture. Before to go ahead though, let's go to the texture2d C++ file and in the constructor, let's store the size of our texture. So far so good, let's finally go ahead and let's bind the vertex and index buffers in the graphics pipeline. Then we can set the calm mode, and after that we can update the data inside the constant buffer and in the end we can bind it always in the graphics pipeline. Of course, don't forget to set the vertex and the pixel shaders. At this point we can pass the height map to the shaders. And last but not least, let's finally call the draw indexed triangle list method. We don't have to do nothing but go to my game C++ file and in the onCreate method, let's remove all the previous entities but the skybox. Let's remove them by commenting the various parts of code. Let's see if it works. And it works! At this point, let's finally create the terrain entity. As usual, don't forget to include the terrain component header file in the all header file. As first thing, let's set the height map. And so let's load our height map texture resource. And at the end, let's pass it in the set height map method. Let's see if it works. And it works! We can finally see our 3D terrain. But as we have already discussed in the introduction, we have to compute normals to generate the lighting correctly. So let's go to the terrain.hlsl file and let's use the so-called central difference approximation method. So far so good. In order to navigate the terrain quickly, let's speed up a bit the movement of our camera. Let's also enlarge the view frustum by setting a far plane of 7000 units. Let's see if it works. And it works! Now we can finally see the terrain enlightened by the sun. Good! The last part we are missing is the coloring. So let's go to the terrain component header file and let's start to add the ground map, that is the texture that will be shown in the ground surface. As usual, let's add the setter and getter methods. At this point we can go to the graphics engine C++ file and in the update method let's also bind the ground texture to the graphics pipeline. In the end, let's go to the terrain.hlsl file and let's define a further texture and its sampler. We don't have to do nothing but replace the white color with the color of the ground texture. The final step to do is to go to my game class, load a ground texture, in this case a grass texture, and set it as the ground map in the terrain component. Let's see if it works. And it works! At this point, let's also add a further texture in the terrain component, and let's call it wall map. Here I have erroneously called it cliff map, but the concept is the same. Let's do the same exactly things we have done previously for the ground map. So far, so good. Now it's the time to use the famous dot product. So let's make the dot product between the normal of the terrain and the y-axis. And if the dot product is less than 0.5, let's use the wall texture, in this case called cliff. At this point, let's go to the My Game class and let's load another texture that here is called ground. Let's set it in the terrain component as wall texture. Let's see if it works. And it works! The only step that remains to do is to blend those textures in order to have a seamless effect. So let's go to the terrain.hlsl file and let's replace the code inside the if with the lerp function seen in the introduction. And it works! Let's change the minimum and maximum values to see how the blending changes. That's all for now, folks. Today we have seen how to create and render a 3D terrain. The next time we will face the making of a 3D ocean. I hope you enjoyed this video. See you soon. Thanks for watching.